Hi, everybody. My name is Paul Taylor. I come from NVIDIA. I'm going to talk about rapids for GPU accelerated data science and geospatial analytics. Um, for those who don't know, NVIDIA Rapids is our suite of data science libraries for bringing GPU acceleration to the data science and engineering ecosystem. So these are going to be the talk today is going to be about our Python libraries. There are also a set of Node libraries which have gotten mentioned a couple times before. Hopefully, I can get through these slides and then maybe show some demos of those near the end if we have time. So Rapids is composed of a set of domain-specific libraries and then general-purpose libraries that you would use in your code, or they're used by these domain-specific libraries. And so, what do I mean by general purpose? Data ETL processes, general machine learning, forest inference, graph analytics. Those are all relatively used in lots of different domains. So they're relatively general purpose, and you might go from solving a problem using the data frame to then doing a graph analytics problem, but you might be working on a supply chain issue. So we've GPU accelerated at each layer in the stack, and so to giving you these high level APIs that are familiar if you're familiar with the PyData ecosystem, and then there's also more specific libraries under the hood for doing things like cybersecurity, geospatial, signal processing, image processing. I'm not going to talk about those today. We're just going to go a little bit of high level overview of just the general purpose libraries, and then see how we use those in our geospatial analytics problems. So the first one I want to talk about is our data frame library. And so NVIDIA, if you know anything about CUDA or the CUDA ecosystem, NVIDIA likes to prefix our libraries with CU if they use CUDA. So a lot of these things are going to have CU in front of the name. So our data frame library is cuDF. It's a data frame library that gives you a pandas-like API in Python, but under the hood, it GPU accelerates all the operations. So if you're familiar in pandas, you take two tabular data sets, you might join them together on some key. cuDF will feel very familiar. You might read in a couple CSVs and join them together on some key, but that join operation is going to be GPU accelerated. And so what that gives you is a lot of times you get not just many percentage speed up over the CPU alternative, is you get many multiple speed up, and sometimes orders of magnitude faster when you run something on the GPU than on the CPU. And the goal is that it should be we can't always provide exactly one-to-one what you might get from pandas or cuDF. Certain things that are fast on the CPU just don't make any sense on the GPU. So, for example, pandas might oftentimes sort its outputs before it returns it to you, and we don't necessarily. The GPU doesn't necessarily care if something's sorted or not. If it's sorted, it might not make it any faster, and so all you're really doing is slowing down that operation by needing to do a subsequent sort afterwards. So there's certain cases like that where it might not be make sense for us to do something, or you might need to sort it afterwards if you're expecting to get what you would get from pandas. But a lot of times, it's exactly what you get back from pandas, just many times faster. So the things that are built into the data frame library are things like string parsing, CSV reading, parquet parsing. And so if you're using an alternative for this talk that I was considering was, I didn't know my GPU could do that, which is a lot of times how I feel when I'm using these libraries is, I didn't know my GPU could do regular expressions. I didn't know my GPU could parse a CSV for me. And so what's neat about this is if you've got these string operations, you can decompose, you can run them on many millions of rows of string data all in parallel and have it return much, much faster than it would on the CPU. So we support reading and writing Parquet, reading and writing CSV, reading and writing Arrow, reading and writing ORC, even experimental support for JSON reading, and that's only getting better. So we're trying to integrate with lots of different data formats and libraries in the PyData ecosystem. And so some other things that you might not know that the GPU can do is compression and decompression. So by using cuDF, you could say read in a Parquet file that has its columns compressed, using the snappy compression format. And so if you're reading, many, many column CSV or many, many column Parquet file, it might make sense to do that column decompression in parallel. And so by using, cuDF, we link to the, NVIDIA decompression libraries to automatically decompress your columns in parallel. So a lot of times we can see some pretty dramatic speedups, all happening underneath the scenes. All you might not even know it's happening. You just see it's faster. And so that's, from a high level, what we're doing inside of our data frame libraries. Another neat thing about our data frame libraries is that we've actually built them into Apache Spark. So there's Spark accelerators. So that uses the same C++ library under the hood. You can then use in Databricks in your Java or Python Spark workflows. So something that might make sense to people who are doing a lot of things in Spark is total cost of ownership. So how can you bring down the cost of each of your Spark jobs? You're running these giant batch jobs. And so we've got actually a tool built into the Spark plugin that can analyze your existing queries and tell you which ones would make sense to run using the GPU accelerated Spark plugin. So the next library is the cuML. It's our machine learning library. It's roughly analogous to scikit-learn. So a lot of the same, machine learning, forest inference, random forest, UMAP, dimensionality reduction, that kind of stuff will be accelerated with cuML. Including it supports multi-node and multi-GPU. So if you've got bigger workloads, you can automatically get that running on multiple GPUs and multiple nodes. Also, we've got our graph analytics library, which is for large-scale graph analytics. So triangle counting, page rank, traditional graph coloring, labeling, traditional graph problems. You use cuGraph. So this slide up here, the graph over there shows scaling PageRank to 2084 GPUs. Sorry, 2048 GPUs. So really, really, really big graphs. We can scale to data center or HPC scale problems. And then finally, a library that's near and dear to my heart because I worked on it directly, Geospatial. So this is what you guys probably care about. GPU accelerating geospatial and analytics workloads. So Geospatial is a library for doing vector processing. We don't really do image processing. So if you got a bunch of satellite data, that's currently not something that Geospatial would be used for. But if you've got a lot of XY coordinates, lat longs, lat longs tied to timestamps where you might need to traverse trajectories, that's the kind of stuff that Geospatial is great for. And so this is roughly analogous to our GeoPandas. This is roughly analogous to GeoPandas in terms of what we're trying to provide. So similar to how cuDF might be analogous to pandas, cuML is analogous to scikit-learn, cuGraph being analogous to NetworkX, Geospatial would be analogous roughly to GeoPandas. So currently it's also focused on 2D operations. We don't really do 3D, although at the C++ layer we have some support for 3D operations. But what you can see is already we can, in this slide, see that we can get some pretty dramatic speedups against what you might be able to get out of GeoPandas, running on the CPU. So, and some workloads don't necessarily make sense to run on the GPU. I'm sure, as lots of people have found out, that if you've got small data, there's just some latency and overhead cost of launching kernels to launching GPU programs. So if you've got sub 1,000 rows in your data set, it might actually just take longer just to launch the program on the GPU. But if you're doing anything bigger than that, it very quickly starts to make sense where you're doing stuff on the GPU. This graph right here, actually not a big fan of the log axis on the left because it doesn't really give you a great. It's an exponential curve, so that's it's a pretty dramatic speed up there. So another thing about Geospatial is we started building in support for the GeoArrow spec. So GeoArrow being this emerging spec that Kyle is going to talk about after this, being an arrow-based format for representing multi-polygons, line strings, multi-line strings, all that stuff in a columnar way. So Geospatial provides a number of indexing and join functions for spatial joins, a number of trajectory functions for deriving trajectories, computing the distances and speeds of them. So the idea, if you've got billions of points, you need to very quickly figure out what the trajectories of all those objects are, and then figure out how fast they were going. that might be something you do in Geospatial. And then spatial, spatial dimension, spatial comparison functions for comparing different geometries together. So this would be one of our, like an example of the spatial predicates. It's an implementation of the DE9IM, if anybody's familiar with the dimensionally extended 9 intersection model, sort of a general standard and sort of language you can use for doing a number of point, line, and polygon comparisons. And so this is an example of a sample accelerated workflow. A lot of these libraries will sort of fit this model where you might have some stuff you do on the CPU, and then you drop into doing the GPU parts, and then you go back into the CPU. And the more you can do on the GPU, the faster it's going to be. So the more parts you can replace with GPU parts, ultimately that's going to translate to a much faster job. And so if you've got, let's say I can do part of it with the GPU, then I have to go back to the CPU, then I have to come back to the GPU and do the rest of it on there. That represents, if we could just bridge those two divides where you can do it all on the GPU, you can dramatically increase the speed of your jobs. So that's what we're trying to provide here with Geospatial. So GPU accelerated I/O, GPU accelerated data frame or ETL operations, and then GPU accelerated geospatial operations. Sort of the architecture of all of our libraries follows this model. We have a high-level Python interface, which you as a user probably want to use. Then underneath the hood, we use Python to translate that into C++ calls, into our underlying C++ APIs. And those C++ APIs, use dynamically linked and have both CUDA device code and C++ code in them. That code ultimately is based on the CUDA driver and runtime APIs. And so theoretically, the Python API doesn't necessarily have to be the only high-level language interface into these C++ interfaces. So that's where some of the Node stuff comes in, where you sort of swap out and say, hey, I'm going to put a Node interface on top of the C++ library, not just have a Python one. Theoretically, you could also have an R interface or a Rust interface or anything else that can link to C++. You should be able to have an interface for. But we provide a Python interface. A little bit about the memory format, the GeoArrow. I don't want to go too much into what Kyle's going to talk about, but it's a columnar format for describing these geometries. So ultimately, you still have all of your x, y coordinates in just giant contiguous buffers, and then you represent the lines, the multi-lines, or the polygons as essentially lists or lists of lists. So it's super fast, super quick to serialize and deserialize, and most importantly, super quick to load and unload from the GPU. And lastly, something new in the latest, this is right hot off the presses, last release, we have this brand new library that's sort of a complement to Geospatial called GeoProj. And this is an implementation, a partial implementation of the PyProj API, which is an API for projections. So allowing you to project from one coordinate system to another coordinate system. Currently, it only is a to and from the WGS84 to UTM standards. So that's the same longitude, latitude that would be used by GPS to universal transverse Mercator, and vice versa. But even though it's only got that implementation, that's the only formats that are supported. You can start to see that we're getting some pretty high returns on the throughput there. So this is 3 orders of magnitude between GeoProj and just regular Python proj running on the CPU. So if you've got some lots and lots and lots and lots and lots of data to project, check out GeoProj. Lots of documentation for deploying Rapids. You can find it all on our website, rapids.ai. These slides are sort of on that site as well. We've got a thing that we're launching called NVIDIA Launchpad. It's a tool for getting a developer environment set up on hosted GPU instances. So this is still early days, and I'm not even sure if I'm supposed to advertise it. But what I've been told is that if there's a significant need, that there's somebody I can talk to and say, hey, this customer is interested. So I can't promise anything, but I can hand you off to the right people. This you could use to they essentially have a VS Code, in the browser interface. You can remote SSH into it, or you can also use it to just launch, Jupyter Notebook servers. And lastly, how to get started with Rapids. There's self-start resources on our website. Uh, you know, Rapids.ai for all the stuff. We got all the docs. It's a very fast-moving project. So stuff that next release might totally change or add brand new features. So definitely check out the roadmaps there if you're needing something. And they're all open source. So if you're so inclined, you can clone them, check them out, and figure out how to build them. I can help you with that and contribute yourself. So that's what I got for slides. Any questions? Martin? Do I have any mind-blowing demos of me? Oh, wow. All right. Well, since you asked. Let's see. So I do. And this one's a fun one from, let me get this over here. So this one is fun because, so this is in our Geospatial notebooks right here. I'm just going to run it in VS Code here. So I'm going to go and click this. Where'd that go? There we go. All right. So here we go. Oh no, it's got to install this. Oh, I thought, dang. I thought I had this already open. Yep. There we go. Wait. Don't do that. Cool. All right. Let's run all these. So this is something that you'll see in our Geospatial data sets. This is linked in one of the slides that I've got up there. What this is going to do is this is going to count stop signs by zip code, which is kind of a neat problem if you think about it. So let's say you've got these data sets where all the stop signs in the US are, right? There are all these points, X's and Y's. And then you've got the zip code boundaries from the census. And you've got the state boundaries from OpenStreetMap. So let's say you wanted to say break down and figure out how many stop signs are in each zip code in a given state, right? And then you're going to visualize that at the very end because visualization is 90% of the demo. But that's a really neat problem which involves essentially a bunch of spatial joins where you have to filter, spatially join all of the query for all the points in every given zip code boundary in every given polygon, and then you ideally like to do that in parallel because you've got thousands and hundreds of thousands of zip codes. So I'm running this demo right here, but one of my favorite things about VS Code is it tells you how long each cell takes to run. So I can just run this ahead of time and we can just look at how long it takes. So this example where we read in our CSV of zip codes, took less than a second to read and parse all that data on the GPU. This is an example of running if we were going to parse that data on the CPU, how long would it have taken? And right here, it's taking 24, 25 seconds. And so that's just to read and parse in this polygon data on the CPU, not even to do any of the spatial join stuff, just to parse the data and load it in. But we've got essentially an implementation of the same parser, but using cuDF string operations, regular expressions on the GPU. And that happened in 3.7 seconds right here. So to go from 24, 25 seconds down to 3.7 seconds to parse the exact same file is pretty radical, I feel like. So lastly, where's this? That's just the parts where we're loading this data, and we haven't even done any of our spatial operations yet. We're just getting to the point where we have the data in memory and can do our spatial operations. And so essentially over here, we write a little class that uses the Geospatial quad tree functions. And down here, we're going to filter these zip codes by its geometric center. So we're going to go and join all of the polygons by essentially select all the polygons by which ones, by where their center is in the state. And so after we've done that, that took 0.7 seconds. And then now we're going to join, actually join the points in each zip code, like the stop signs in each zip code with the zip code polygons to figure out, hey, how many stop signs are in each zip code. And that took half a second. And so, and you can see here's all each row right there is an individual stop sign. And then we have our zip code column right here. And then we're just going to count. And the neat thing about this is counting how many stop signs are in a zip code once we've done this spatial join is really just kind of SQL count distinct, right? It's a group by operation, right? So that took 0 seconds. Like Jupyter couldn't even track it. And finally, we've got our visualization down here, um, where this VS Code might start to get upset with me. Because we're using PyDeck right here to visualize, and this file that the PyDeck generates is 270 megabytes of GeoJSON. But here we go. In California, here's the data that we copied to host, and now we can see uh, who has the most zip codes. It looks like Sacramento, or who has the most stop signs? Looks like Sacramento, maybe? I don't know that zip code by heart, but that one looks like the tallest one to me. Yeah, that's just using the Python stuff. I've got a couple other demos with Node stuff, but I think I'm running up against my time. So, yes. 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 Okay, I promised I wouldn't show these demos, but hold on. Yeah. So this was if anybody was familiar with the talk I gave last time in where'd that go? My multiple desktops are messing with me. Is it on that side? Do you guys see it? Oh, where is it? All right, let me try to open it again. Maybe I'll open it on my machine and then drag it over there on my screen. So this is an example where we here we go. Cool. Where what we've got is we've actually got, this is using the Geospatial quad tree to do the point and polygon hit test. So every time I mouse, and I'm going to move my machine up, my thing over here so you can see this terminal, which I really like. Watch this terminal down there. So as I'm mousing over each of these taxi zones, I'm actually running a quad tree point and polygon hit test using the polygon that your mouse is currently moused over. I'm querying for all of the points that are in that polygon. And that query happens on 170 million points because this is 2009's taxi zones data set from New York City. And so the reason I say watch this is because this hit test is happening pretty quick. 20 milliseconds, 5 milliseconds. Honestly, the rendering time is the lag. So that's neat. So that's actually running, this is running an OpenGL. This is using DeckGL to render, but we've got a faked out API that makes DeckGL think it's running in a browser. Now, it doesn't give you all the things a browser would give you. It just gives you the OpenGL context, but you can already see what you're able to do. Another one that's fun is this isn't just a trick. This actually does do, it does a lot more than just, where'd that go? Is it over on the left? There we go. All right. So this is actually a similar demo, but it's using the OpenStreetMap data in the New York City streets. So we're using, this is using the CSV, the street data from the CSV, and then using a similar technique using string parsing in cuDF to parse that into a geometry format, the GeoArrow geometry format. So then we can use that GeoArrow geometry format and give it to the streets layer in DeckGL. So we're using, both of these demos we're using the MapLibra stuff. So we've got the vector tiles over here through MapLibra, which thank you for that, everybody who's responsible for that. And what's neat is we're just highlighting them as we mouse over. What's cool, what I really like about this demo is that it connects unconnected streets. So streets that in the original data set say that they're the same street and are the same street, but aren't physically connected, right? A street that might start in one location and then pick up later somewhere else. Is by parsing and doing this parsing, we're actually adding some information that was lost in the original translation or representation of this data set. So both of these demos are available, or all these demos and at least one more are available in my GitHub. There's a Rapids Carto talk for me, and you can ask me for that URL afterwards. Thank you.